The next problem is to find the IDFT for the sequence x of k, which is equal to 5, 0, 1 minus j, 0, 1, 0, 1 plus j and 0. So from the length of the sequence we observe that the number of points is 8, hence capital N is taken to be 8. The problem is to find IDFT, hence from the definition of IDFT we know that IDFT of x of k is equal to x of n equals 1 by n times summation k between 0 to n minus 1 x of k into wn to the power of minus kn, where n value lies between 0 to n minus 1. Now since n value is 8, let's substitute the value 8 in the above equation. We get x of n is equal to 1 by 8 times summation k is equal to 0 to 7 x of k w8 to the power of minus kn. Expanding the summation yields you a series which has x of k as the input and w8 to the power of various powers of minus n. So the first term is raised to 0, next we have to the power of minus n, next we have minus 2n, minus 3n, minus 4n till the last term which is minus 7n. Next step, let us substitute the inputs that we have. Fortunately for us, 4 of the inputs are zeros and these terms are eliminated. So we are left with 4 terms here and we have to simplify it, and you can write it in the form as shown here. Now to proceed further, as you know, we have to solve this for n value which is 0 to 7, that is totally 8 points. We have to compute the twiddle factors. Now we know that for n is equal to 8, the twiddle factors will be lying on the complex plane on the unit circle. So they all lie on the unit circle. The circle is not shown here, but please understand it's on the unit circle. And they have a radius which is equal to 1, obviously. And the whole complex plane is divided into 8 parts because n is equal to 8. Now, you know the point of reference is on the right side of the real axis. So from this point, since the problem is IDFT, we travel in a direction which is anti-clockwise. The twiddle factor powers that we need are all negative. So we have w8 to the power of minus 1, w8 to the power of minus 2, w8 to the power of minus 3 and so on. So traveling in the anti-clockwise direction will fetch us the various numbers. The values can be remembered in a very simple fashion as 1 by root 2 plus j 1 by root 2, or in terms of numbers it is 0.707 plus j 0.707. On the basis of the quadrant you can easily calculate the value because the numbers are same but only the sign depending on the quadrant will vary. So in the third quadrant we know both are negative. Here the real part is positive, imaginary is negative. Here the real part is negative, imaginary is positive. Like this we can determine the values, and we already know the values here are 1, j, minus 1 and minus j. So we have the first 8 twiddle factor powers. If the problem was for a DFT, then we should have traveled in a direction which is clockwise direction. We have to use the formula for the DFT, and the rest of the procedure will be quite similar. Substituting for the different values of n, let's start with n is equal to 0. The equation for x of 0 simplifies and you get the result as 8 by 8 and the result is 1. Next, for n is equal to 1, similarly, when you substitute and put the various values of twiddle factors, the simplification here will give you a result which is 6 by 8 and the answer is 3 by 4. Next, when you put n is equal to 2, similar substitution will give you the result which is 1 by 8 into 4. The answer is 1 by 2. The next value n is equal to 3 will give you the result which is equal to 2 by 8, it is 1 by 4. Students, please be very careful when you are doing complex multiplications and additions. When you are doing the simplification part, always do it carefully and if possible, do check it. Now for n is equal to 4, similarly, we are going to substitute the values and we're going to simplify, and the answer we get is finally 1. For x of 5, the result is 3 by 4. For x of 6, in a similar fashion, the result you find out to be 4 by 8 or 1 by 2. And the last value, n is equal to 7, yields a result that is equal to 2 by 8, which is 1 by 4. And finally, you can list out the value that you obtained. X of n is equal to 1, 3 by 4, 1 by 2, 1 by 4, 1, 3 by 4, 1 by 2, 1 by 4. So I encourage the students to please try out the problems so that you can gain confidence in doing things on your own. The next problem number 5. Find DFT of the sequence x of n, which is equal to 1 for n value between 0 to 2 and 0 otherwise. For capital N is equal to 8, plot the magnitude of x of k and the angle of x of k. So we observe that since the definition says for n 0 till 2, that is totally 3 points, the value you will get is 1. And for the remaining points, you get a value which is equal to 0. Now for this, if you perform the DFT calculation, the method will be quite similar and you get 8 points as the result. So the steps are not shown here, but definitely you can follow the DFT calculation method as has been described and apply the various twiddle factors and the inputs, solve and get this result shown here. Now for this, to find the magnitude, as we are aware, for a complex number, the magnitude is given as square root of a square plus b square, where the complex number is a plus jb, and the angle is given as tan inverse of b by a. So the magnitude can be easily computed from this complex number. If possible, you can change to polar form also. In polar, you get the magnitude separately and the angle separately. So you can list out which are the various magnitudes and which are the various angles. So this can be plotted in the form of a graph. So horizontal axis k, vertical axis is magnitude of x of k. So here is the sequence which we have plotted. Similarly, the angle also, if you want, you can plot it. The next numerical here is to find the DFT of x of n equals to delta of n. This is a pretty simple problem provided you know the definition of delta of n. Now in the problem, since you are looking for the DFT, first from definition of DFT, we have DFT of x of n is equal to x of k given by the summation here. Now since we want to find DFT of the input delta of n, so substitute the value x of n is equal to delta of n in both sides of the equation. Therefore, the input is now changed to delta of n. Now from the definition of unit impulse function, delta of n is equal to 1 at n is equal to 0, and it is 0 for n not equal to 0. Therefore, now when you insert this particular condition in the previous equation, there is no longer need for the summation because there is only one single term at which delta of n has its existence. So it exists only at n is equal to 0 and its value there is 1. So therefore, the replacement for delta of n is only for n is equal to 0. Therefore, we write it as delta of 0 into wn to the power of 0. wn to the power of 0 we know is 1 and delta of 0 is also 1 by definition of unit impulse function. Therefore, we have solved the DFT of delta of n is equal to 1. This numerical is a simple variant of the previous one because there we had solved for delta of n. Here the input x of n is shifted unit impulse function given by delta of n minus n naught, where n naught is the shift. Now from the definition of DFT, once again here we take the definition. In this definition, x of n we are substituting as delta of n minus n naught. Therefore, we can see that DFT of delta of n minus n naught will be, on substituting x of n in the above equation, we get this. Now, if we understand the definition and the significance of delta of n minus n naught, then the problem is very simple. So we are aware that delta of n minus n naught is nothing but a shifted version of delta of n. Therefore, the single magnitude point which was at n is equal to 0 is now shifted to n is equal to n naught because we are shifted by the amount n naught. Now, as per the definition, we know the value is 1 at n is equal to n naught and 0 for any other value of n which is not equal to n naught. Therefore, once again, this summation has existence at only one point, that is n is equal to n naught. And when you substitute the value 1, the result of substitution will look something like this. So there's no need of summation now. We are taking only n is equal to 0. Therefore, we have delta of 0 wn to the power of kn naught because n is equal to n naught. And after putting the appropriate values, we can observe that the DFT of delta of n minus n naught is nothing but wn to the power of kn naught. So this is the result. On similar lines, we can say that delta of n plus n naught will have a DFT given by wn to the power of minus k n naught. The next numerical is to find n-point DFT of x of n, which is equal to e power of j2 pi by n k naught n. Now once again here, from the definition of DFT, we can write the definition as DFT of x of n, x of k, and it's given by the summation. The DFT of the input that is given, that is e power of j2 pi by n k naught n, can be calculated by replacing x of n with that particular input. Then real factors, the exponents, they can be combined to write it in the form of e power of minus j2 pi by n k minus k naught whole power of n. The reason for arranging it in this particular fashion is we want to write it in the form of a finite series as shown here, where the initial value of index is 0, the highest term we have is capital N, and it's a series of a with various different powers of n. And the solving this particular thing, the simplification is given as a power of n plus 1. So you check the highest term, add 1 to it, minus 1 divided by a minus 1. Alternatively, we can also write it in the form of 1 minus a power of n plus 1 divided by 1 minus a. So if you want, you can take a minus as a common thing, and minus will cancel, and you can get an arrangement like what is shown here. So to continue solving this particular problem, now we can express the above summation. We have found that the a value is the value in the bracket. So let us substitute it here. So the expression becomes 1 minus a power of n, because the highest term limit is n minus 1, 1 more than that, divide by 1 minus e power of minus j2 pi by n into k minus k naught. Now this expression, if you try to solve it for k is equal to k naught, when you put k is equal to k naught, this term becomes 0, and the second term all becomes 0, and in anything to the power of 0, see, the power has become 0, anything to the power of 0 is said to be 1. So the numerator is 1 minus 1, which is 0, and denominator is also 1 minus 1, which is 0. Therefore, it is said to be indeterminate. Now, to simplify this particular problem, we can apply a method which is called as L'Hopital's method. Here, it involves differentiating the numerator and denominator with respect to k, and then substituting the value k is equal to k naught. Therefore, on differentiating, the term will become something like this. So you can see that the differentiation of 1 is 0 minus, when you differentiate an exponent, you get the same exponent, and in addition to that, we will have the value minus j2 pi. So minus j2 pi into exponent, divide by minus j2 pi by n into the exponent shown here, and we have to substitute the value k is equal to k naught. So when you put the value k is equal to k naught, the equation simplifies, and numerator becomes j2 pi divide, and the denominator is j2 pi by n. So simplifying it, solving, we observe that the answer we get at k is equal to k naught is equal to n. So therefore, the expression for x of k could be written as it's equal to n at k is equal to k naught, and for the rest of the values it is equal to 0. Or alternatively, x of k is equal to n times delta of k minus k naught. This is at k is equal to k naught. And in the form of expression we can also write like this: x of k is 1 at k is equal to k naught and 0 for k not equal to k naught. So for any value where k and k naught are different, the answer, the resultant value you get is always 0. Now we can solve a similar looking numerical. Here we have taken an exponent. You can take a similar exponent, just change the sign and it becomes a different problem. In the next numerical, we have a similar looking problem, but x of n is e power of minus j2 pi by n k naught n. So we have a power which is negative. So the approach will be quite similar. We want to find DFT of this particular term. Therefore, inserting the value of the input in the DFT equation, and further we can combine the two powers by collecting the common terms. Once again, the attempt is to express it in the form of a power of n. And for the finite series, we know the answer is 1 minus a power of n divided by 1 minus a. And we can do the necessary substitution and simplify, and ultimately you will get the result as n times delta of k plus k naught. So the value exists at k is equal to minus k naught. Everywhere else the answer is 0. Once again, we are tabulating it as x of k is equal to capital N at k equals to minus k naught, and 0 at k is equal to not equal to minus k naught. The next problem here is to find the endpoint DFT of x of n is equal to cos 2 pi k naught n by capital N. Once again here, for the DFT problem, we involve the definition of the DFT, and from the definition we can write the following. Now, x of n is equal to cos 2 pi k naught n by capital N. So we have to substitute the value of x of n. So changing x of n, this is what we get. Next, we are aware that cos of theta is equal to e power of j theta minus e power of minus j theta divided by 2j. So on substituting the value of cos, we can write I'm sorry, correction please. Cos theta is equal to e power of j theta plus e power of minus j theta by 2. Therefore, the substitution will be cos of the quantity inside the bracket, that is theta. So we have e power of j theta plus e power of minus j theta divided by 2. Kindly ignore the symbols which are written in blue color. They are meant for a small variation of the same problem. So then twiddle factor is also expressed in the form of exponent. So we can combine the two exponents and we can get a term like this. Therefore, we'll have 1 by 2 common, and then we have e power of the term shown here, and then we have e power of negative j2 pi by n k plus k naught term. Now, as we have learned from the previous problems, the problem cannot be solved directly, but you can treat it to be a finite series in terms of a power of n, and it also results in an indeterminate form when you apply k is equal to k naught and k equals to minus k naught. Therefore, you have to follow the entire steps, and finally you will end up with the answer 1 by 2 times n times delta of k minus k naught plus n times delta of k plus k naught. This is the DFT of cos 2 pi k naught n divided by capital N. Now, a very similar looking problem we will find is for sine. Instead of cos, if you're given x of n is sine 2 pi k naught n by n, then the substitution will be sine theta is equal to e power of j theta minus e power of minus j theta divided by 2j. As you can see here, the same I have tried to highlight here in the problem by illustrating it in blue. So you get a negative here, you'll get a j here, and this will be minus, you'll have the extra j. The simplification proceed in a similar fashion, but you'll have minus here and you'll have a j. Therefore, the result for sine is 1 by 2j into n times delta of k minus k naught minus n times delta of k plus k naught. This is how you can solve this particular problem.
Thank you all.